Welcome back to Cured to Last. This one's specifically for you folks in the concrete masonry and hardscapes industry. Yeah, we're zeroing in today. We're looking at modernizing concrete curing chambers, and we've got this great report analyzing upgrades at 3 plants, all located within the same production facility in Ireland, named here as HESS1, HESS2, and HESS3. Here we go.
Okay, let's dive right into it. We're taking a deep look today at modernizing concrete curing chambers.
Yeah, our source material.
Yep.
It's a specific report, yeah. Looking at upgrades in Ireland at 3 plants, HESS1, 2, and 3, part of one facility.
Exactly. So think of this as your shortcut, really, to understanding how these kinds of upgrades, well, how they could potentially boost efficiency, improve quality.
And crucially, manage costs. That's always a big one in this industry.
Right. And, this report has some genuinely surprising findings.
Oh, it definitely does. Like the potential to actually use less cement.
Yeah.
Significantly less. Just by having better control over the environment, that really jumped out at me.
Me too. So, okay, the report starts right at the beginning, kind of walks us through the basic product flow. You've got the wet side and the dry side.
Right. The wet side, that's where the fresh concrete products, come off the block machine onto their boards or pallets. Then they move into the curing chamber.
Simple enough. And the dry side is just after curing's done. Boards come out, products ready for packaging or, whatever's next. Secondary processing sometimes.
And the report mentions the automated movement, too. The elevator stacking the boards. The finger car moving those stacks into the racks inside a chamber. And then the lowerator on the flip side to unstack them.
It's a pretty slick automated dance, isn't it? And the block machine itself, intense vibration, hydraulic pressure, compacting that mix.
And it's fast. The report clocks the cycle time at just, 12 to 20 seconds per board. Efficiency is definitely key.
Absolutely. Now, before we get into the chambers themselves, the report quickly touches on efflorescence.
Ah, yes, the white powder problem. What's the report's quick take on the cause?
It's basically calcium hydroxide, which comes from the cement hydration. If moisture moves through the concrete, carries it to the surface.
It reacts with coheros in the air.
Exactly. Forms calcium carbonate. That's the white stuff you see.
So managing that moisture movement during the cure is really fundamental to preventing it.
Precisely. Better control, less salt migration. Simple as that, almost.
Okay, so all this really starts with understanding what concrete curing is. It's not just letting it dry out, is it?
No, not at all. And that's a really important distinction the report makes. Curing is active. It's about providing, the optimal conditions, specifically moisture, temperature, and time.
Right, for the cement to hydrate properly.
Yeah, hydration, that key chemical reaction, Portland cement plus water.
Forms the hydrates. The glue, essentially, that binds the aggregates. That's where the strength and hardness come from.
So controlled curing is like actively managing those conditions to speed up and optimize that whole gluing process.
Exactly. Aiming for faster strength gain, yeah, but also more consistent color, a denser, less porous product overall. All signs of, better quality.
And the report really shows why that control matters by looking at the evolution of curing systems. It breaks it down into 3 main types.
Right. They start with the most basic. The open rack air dry systems.
Which is basically just racks sitting out, exposed to, whatever the weather's doing.
Okay, so the pros there are pretty obvious. Low initial cost, simple setup, hardly any fuel costs.
Easy visibility, too. You can just walk up and see the product.
Right. But, and this is but the report highlights, the major downside is the complete lack of control. You're totally at the mercy of ambient conditions.
Leading to unpredictable efflorescence, and color variations, depending on where a product is in the rack or even just the time of day.
Exactly. And they note that this lack of control means hydration isn't really optimized, so you potentially get a less dense, more porous product.
Condensation can be a real headache, too, depending on humidity swings. Turnaround times are longer, naturally, because you can't speed things up reliably.
And the report suggests you might even need to compensate in your mix design, maybe use more cement, just because the curing isn't ideal. It's a classic trade-off, isn't it? Cost versus control and quality.
Definitely. Which brings us to the next step they discuss, these semi-open curing chambers.
Yeah, these are individual chambers, often insulated, usually with roller doors. The report mentions a typical 4-phase process.
Right, like a preset period, then ramping up the temperature, holding it there for a dwell phase, and then cooling down. More structured.
Much more. So the big advantages moving up from open racks, Well, they integrate better into the plant building itself. Your machinery, like the finger car, isn't out in the weather.
That's a big plus.
And you get individual chamber control, which helps with batch management, better heat and moisture retention than open racks, so potentially better throughput.
It sounds like a definite improvement. But what were the sort of lingering issues, the drawbacks that maybe pushed facilities like HESS to look even further?
Well, the report notes energy costs are still relatively high compared to the most advanced systems. And you can still get some slight temperature variations within a rack inside one chamber. Plus, the roller doors themselves, they can be a maintenance point. And while it's better, condensation can still sometimes be an issue if the control isn't absolutely precise.
Right. Okay, so this brings us to the main event, really. The system HESS invested in, the focus of the report, fully enclosed, single atmosphere chambers.
This is the top tier. A completely sealed, heavily insulated room. The environment inside is kept incredibly consistent. Temperature is rock steady. The report says 35 to 40 degrees Celsius. That's about 95 to 105 Fahrenheit.
And humidity.
Constantly high, between 80% and 95%. And crucially, this isn't just during the curing cycle. It's maintained 247, 365 days a year.
Wow. That's serious commitment to stability. How on earth do they manage that level of precision?
It takes a pretty sophisticated air handling unit, an AHU. It circulates the air, heats it, often using a heat exchanger for energy recovery.
Smart.
And this is key. It uses a hot fog moisture addition system. The report mentions auto fog specifically. That gives you very precise humidity control. And if it gets too humid, there's an exhaust ventilator.
So actively adding moisture, actively removing it if needed, total control.
Exactly. And the report details how they circulate this conditioned air, even in the machinery areas within the chamber. And they use these horizontal air curtains at the openings.
Air curtains, like invisible doors, to stop the conditioned air escaping.
Precisely. They create an air barrier to minimize energy and humidity loss when stuff moves in or out. And yeah, the AHUs needed for this, like the ones at HESS 2 and 3, they're substantial pieces of kit.
Okay, so with all that engineering, what's the big payoff? What does the report say is the number one benefit?
Unbeatable product consistency. That's the headline. Every single product, no matter where it is in that chamber, experiences the exact same curing conditions, minute by minute, day by day.
That makes perfect sense. And the report made a slightly surprising point about the initial build cost too, didn't it?
Yeah, depending on the scale, it can sometimes actually be lower than building lots of individual semi-open chambers. But the really significant savings, they often come later in the operating costs. Much lower energy use, less maintenance compared to running multiple semi-open units.
And this consistency, this optimal environment, how does that link back to the concrete mix itself, the recipe?
Now that's where it gets really interesting. That stable, ideal curing environment. It gives you the confidence to really fine-tune your mix design.
Meaning
You can potentially use less of the expensive stuff, specifically less Portland cement, and still reliably hit or even exceed your strength targets. Plus, the constant warmth eliminates the risk of surface drying on fresh concrete. That can be a problem otherwise.
that potential cement saving is huge. But hang on, what about all the machinery inside this warm, humid place? Doesn't it just, rust away?
That's a very fair question, a common concern.
Yeah.
But the report addresses it head on. It states that even though the air is warm and humid, the surfaces and equipment inside the chamber are kept completely dry.
How does that work?
Because the humidity is controlled in the air itself. It's not allowed to reach the dew point where it would condense on surfaces, so no standing water, no dripping condensing.
Oh, I see.
Which means, according to the report, no need for special anti-corrosion painting or galvanizing. Just routine lubrication, standard maintenance, and visibility inside is apparently perfect.
Okay, impressive. Let's get into the numbers, though. The quantified results from those HESS upgrades. Why did HES 2 and 3 actually decide to make this big switch?
Well, the report mentions an energy survey flagged their older semi-open systems for using excessive fuel. And they also had issues with slower than ideal product turnaround times.
And they already had a working example next door, right? HES 1 had put in a single atmosphere system way back in 2008.
Exactly. So that served as a benchmark. The analysis looked at running costs, fuel, electricity, but also production throughput, how much faster they could cure things.
And changes in the concrete recipes, cement, pigments.
Yep. And the overall impact on product quality, consistency, density, strength gain, efflorescence, reducing wastage, the whole picture.
And the report made that big claim about cement reduction, up to 10% potential.
It did. And they actually saw results backing that up. There's a specific example from HESS3 for standard engineering block. They cut the rapid hardening Portland cement, the RHPC, from 300 kilos per mix down to 260 kilos.
Wow, okay, let me just, 300 down to 260, that's 40 kilos less. That's more than 13% reduction.
Over 13%, yeah. And when the report mentions RHPC costs around 86 euros a ton, well, you can see how quickly those savings add up. That's a serious impact on material costs.
Absolutely huge. Okay, so let's dig into the science a bit. Why does this work so well? That humidity control seems critical.
It really is. And it's all about understanding relative humidity, RH, and how it's tied directly to temperature.
How does that play out inside the curing chamber then?
The report uses a great illustration. Imagine you have 1 cubic meter of air, and it contains 16 grams of water vapor. Now, at 20 degrees C, that's around 68 Fahrenheit.
Okay.
That air is almost saturated. It's at about 93% relative humidity. But take that exact same cubic meter of air with the same 16 grams of water and heat it up to 40 degrees C, 104 Fahrenheit.
What happens to the RH?
It plummets down to just 31% RH.
Because the warmer air can hold much more moisture before it feels full, like a thirstier sponge.
Exactly, a much thirstier sponge. And why is low RH at high temperature bad for fresh concrete? Because that thirsty air will literally pull moisture out of the concrete surface. It wicks it away.
Which messes up the hydration we talked about earlier, the gluing process.
Completely. Stops the cement reacting fully, leads to weaker, more permeable concrete. The report even quantifies it. For a big 5,000 cubic meter chamber, you need about 170 liters more water vapor just to saturate the air at 40 C compared to 20 C.
Wow.
And if your fogging system isn't actively adding that moisture to the air, the concrete will try to provide it, drying out its surface in the process.
Okay, so high controlled humidity is absolutely key. What about air movement? The air velocity across the product surface, is that important too?
Also critical. And it's a balancing act. Too little air movement isn't good. You get stagnant pockets, inconsistent temperatures, maybe localized condensation.
Which can cause color variations, right? And maybe secondary efflorescence later on.
Precisely. But then again, too much air movement is also a problem. High velocity blowing across the surface.
What does that do?
Causes uneven evaporation. So again, you get color inconsistencies, maybe poor surface density, higher permeability, and potentially more secondary efflorescence. You're really looking for that Goldilocks zone. Just right.
So what is that sweet spot? What kind of airspeed are we talking about according to the report?
Generally, they suggest aiming for no more than about 1 meter per second directly over the concrete surface. Maybe even less, like half a meter per second, particularly if you're using surface sealers on the wet side.
And how do you actually achieve that very gentle, even flow across a massive chamber full of racks? It sounds tricky.
It's all in the design of the air distribution. Instead of just blasting air from a few points, you use many more air outlets and inlets placed strategically.
So you distribute the load.
Exactly. Deliver the conditioned air more evenly, but at a much lower speed from each individual point. That ensures a gentle, consistent flow across all the product surfaces, not high-velocity jets hitting some areas and missing others.
Okay, right. So pulling all these threads together, the tech, the science, the HESS results, what's the core takeaway for someone listening who might be thinking about modernizing their own curing setup?
I think the main message from this report is incredibly compelling. Modern, fully enclosed, single atmosphere systems. They offer really significant quantifiable advantages.
And those advantages hit the bottom line, don't they? We've got the potential cost savings from lower energy use, sure, but perhaps most dramatically, that potential for using significantly less cement. That 13% plus feature from HESS is hard to ignore.
It really is. And beyond the cost savings, it's about the step change in product quality and consistency. Less efflorescence, reliable color, better density, reduced wastage.
Which all adds up to faster, much more reliable production throughput too, right?
Yeah.
Making better stuff, potentially cheaper, and getting it out the door quicker.
Exactly. You're hitting all the key metrics. It makes a very strong case. This report really gives you a valuable shortcut to understanding the real-world benefits.
Yeah, we've tried to distill the key points from this insightful report for you. So what does this all actually mean for your operation?
Well, think about that potential for over 13% cement reduction that we saw in the HESS example.
What would achieving something similar actually mean for your annual material costs? How does that potential savings stack up against the kind of investment needed for an upgraded curing system like these? That's the crucial calculation, isn't it? The one this report really prompts you to explore internally.
If you enjoyed listening to this episode of Cured to Last and want to read the report mentioned, please contact us via the contact form link in the episode description. Thanks to everyone listening. Check out future episodes to learn more about concrete curing practices. As we say here at Cure to Last, curing smarter means building stronger.